All right, welcome everyone, whoever is online already. As I said yesterday, if you don't mind turning on your video, I appreciate it. You don't have to, it just makes me feel better. Makes it easier for me to lecture. Otherwise, I only see myself and hear myself. Again, if you feel free to use the chat, but it might take me a while to see your question. You can just say, excuse me, and then ask your question, no problem. Any questions from last time? So this is the last slide that I had. We just got started on, after I did the slides on the logistics of the class and the material that I'm going to cover, I got started on some general introduction. I wouldn't say this is the actual material yet, but I'm just going to give you a feel for what this class is all about. And I gave you sort of a loose definition of a dynamical system, which is not that loose. I didn't list it as a definition, but it all has its major elements. Basically, it talked about discrete dynamical systems. Again, it's a triplet, a dynamical system. You have to have a phase space, you have to from which the dynamic variable comes, then the space of the evolutionary variable, which is continuous or discrete time. Although in some cases, in fact, for certain partial differential equations, you can formulate the problem so that the evolutionary variable becomes space itself. So that's also not impossible. In this class, it's going to be mostly or exclusively time, but very importantly, then you need an evolution rule, which tells you that as a function of the time ticking, how are you moving from one given state of the dynamical system to another state of the same dynamical system. So that other state has to be in the same space. Okay. I just want to move this bar a bit out of the way. Sorry, if I can. Good. No, I can't. So how do I do this? Yeah, better. Okay. And then then we talked about distinguishing two dynamical system types based on the nature of the evolutionary variable, either discrete dynamical system whereby you're hopping discretely in time, or a continuous dynamical system where you would be evolving continuously along trajectories. Okay. And we started looking into this a little bit more in the case of discrete dynamical systems, where it's generally most of the results are for cases when it's defined by an explicit evolution rule, where the next state is a function of the current state plus the current time. And if that evolution rule doesn't depend on time, then we call the evolution autonomous. So the system evolves by itself. It doesn't need any, it needs no checking of what the time is. It always takes place the same way. In that case, we're talking about an iterated mapping for the discrete dynamical system. I gave you as an example the one-dimensional case, which admits a very easy geometric visualization. You can, in fact, construct the dynamics very quickly, qualitatively. And I did that because I want to give you a flavor of this class. Normally, somebody gives you a recursion like that, and it can be vastly more complicated than this. Then by, in other areas, you would really start doing numerics, and you would be proud how fast you coded it up in MATLAB at one line. And then for a given initial condition, you would get a result, right? For another initial condition, you could do statistics on that, or you could pull out your knowledge of series from mathematics that you may have learned either here or in high school, and try to do tricks and so on, which would be you either works or it doesn't. Or you can just take a general approach and say, what I'm really interested in is what's going to happen long term. What is the overall qualitative nature of this dynamical system? Is this, for instance, a good model for what I have in mind? And I just told you that the one quick tool for that is you graph the right-hand side and use this cobweb diagram approach, whereby you can very quickly see if you're converging to stable fixed points. You see their domain of attraction. You see unstable fixed points if there exists. Now, there are also more complicated things that you may not see immediately, but then you realize immediately that, hey, the dynamics can be more complicated. I also pointed out here that the evolution rule may not be running in backward time, because I have no problem iterating this in forward time. But when I try to undo this at this point, right, I actually have a problem because there are two pre-images here. I could either come down here or I could come down there. Okay, and depending on that, my problem will then also continue later on. So at most of these backward steps, so I will have two choices, right? So it's not just, there are two trajectories running and colliding and not more. In fact, there will be, in most cases, infinitely many that join up at various points, right? So the backward evolution, even in this simple example, is not well defined. That's related to the non-invertibility of this function, as I have given. This would not happen if we had an invertible one-to-one function. So the evolution rule is not invertible, but it's a perfectly fine evolution rule in forward time. Okay, would there be any questions related to this? What I've covered so far? If not, I just thought I would spend a little bit of time just showing you, maybe just sketching you further examples and along these lines. So the this might suggest that this is life in the life of one-dimensional discrete dynamical systems, that you're either hopping towards a stable equilibrium point or you're moving away from one. But in fact, already one-dimensional discrete dynamical systems can be incredibly complicated. So I will just note here, although we have not defined it, and I don't know when we'll get to that, that 1D discrete dynamical systems can already be chaotic. Okay, and in fact, one example of that it turns out is, I just sketch it because again, in this business, not the equations are actually very often, the specific form of equations are not even that important. It's more like the qualitative features of the equations that matter, right? So one possibility would be, it turns out, if you play this cobweb game, and again, to play the game, I need to have the 45-degree line here set up, okay, which I do now. And let me look at the center line here. And amazingly, already this map, whose graph I'm attempting to graph, is basically an upside down parabola which goes up really steep. So not every parabola will necessarily work, but something that's really steep. Okay, so it kind of has a plateau up here. What I'm aiming for, in fact, if you attempt to draw this, you may remember from last time that what determines ultimately the stability of a fixed point here is how steep the function is there. So the derivative of the function, if it's a smooth function, has to be larger than 1 in norm. So this only works, what I'm saying now, if at this point, which is clearly a fixed point right here, and this point, but at both points, the derivative of the function has to be larger than 1 in norm. Okay, so if this is graph of f, okay, and the fixed points are, you know, x star I, all right, and this is sort of x star 2, and this is x star 1, which is actually, say, 0 in this case, if this runs from 0 to 1. Okay, so assume that the prime of f at these fixed points in norm is larger than 1. Okay, so in that case, if you play this game, you start something very close, right? You see it will go away. But also, if you start something close to this fixed point here and you play the game, then you also go away, right? So there's no obvious resting place for you. Okay, hopefully I did this. Did I do this correctly? So I need to evaluate this right. So see, you get thrown out. And there's no obvious target for you. So this actually turns out to be a chaotic map. And it is not a proof what I've done here, but one thing that you can immediately notice just by sketching this, that this dynamics will not settle down on a fixed point. Okay, and note that I have not even given you a formula for this dynamical system. All right, and yet I can immediately say that this will be really doing some interesting dynamics, not settling down a fixed point. It turns out to be even chaotic if you play with this for quite a while. But again, if you don't have these tools and you don't have this way of looking at it, then you will have a really hard time, because you do numerical simulations, you do one, and maybe you don't see it settle down, and then you're another one, and you're another one, but it's just still three initial conditions, right? So at best, you will be, you know, starting to guess what's happening, whereas here, you in fact even see the reason and the limit, or what you need to change in the system to change that uncertain outcome completely. So you can in fact just deform this graph and make sure that at some point you deform it in a way that this derivative here is not as large as now. So for instance, if I did this, right, then all of a sudden that fixed point would become stable, and that will be the obvious attractor into which you expect to settle down, right? And you would even know what that critical limit is. So this is the kind of insight that you get from the geometric approach. So this turns out to be a chaotic mapping. Okay. Another example would be, for instance, maybe I covered those later, because you could ask, all right, but well, and I'll just say that for that. Another example. Of a 1D chaotic discrete dynamical system, which is actually would be the binary encoding map of a number in the interval 0, 1. So basically, if you want to write an x equals, and this is not a decimal point, but a binary point, which means that I want to have a binary representation of the function. You will see zeros and ones, but each digit represents not a negative power of 10, but a negative power of 1/2. So the first one is how many times I have to take 1/2. The second one is how many times I have to take 1/4, and so on. So I will be thinking of x as a sum, as an infinite sum of these xi's divided by 2 to the I going from 1 to infinity. So that would be the binary expansion of x. And then symbolically, I write these digits, x3, and the xi's can only take 0 to 1. So the map that does the job to generate this expansion is, because it's not so immediately obvious how you would do that, right? Conceptually obvious, but so instead of using inverse powers of 10 as we use for decimal representations, how would you encode binarily the number, right? And it's the same, again, the same principle. This tells you how many times you have to take 1/2, how many times you have to take 1/4, and so on. You see that from here, right? But a map that actually would generate this sequence for you is this map. So you would get xn plus 1 equals 2xn mod 1. So if you run this sequence, okay, then you have to first, figure out the initial condition. But you run this sequence, it does give you an encoding of a binary number. I'll cover this more when I talk about chaotic dynamics potentially in the second half of this semester. But I just wanted to give you the sketch of this mapping as an example, because even the cobweb diagram can already give you some idea that this is a complex mapping, but it's a useful mapping too. So the way this looks, again, this is the 1/2 line here. So this is 1, 0, 1, 0. And the graph of the mapping, 2x mod 1, right? So I draw this line here. That's empty there. And do another one here. Completely benign, because innocent looking, because this is in fact a linear, piecewise linear mapping, okay? But if you then try to do the cobweb diagram, and I'm just showing you the usefulness of these simple geometric tools, because if this is all you have, and you take a completely numerical, programming-driven view on this, which is, by the way, very common these days, right? Because we got pampered, we can compute anything we want, right? Practically, certainly things of this order. And I'll do various graphs and statistical evaluations, and I'll make conjectures, right? If you just sort of step back a little bit and you say, all right, what do I know about the fundamentals of this dynamical system? What does it look like in the phase space? Then you say, all right, so I have an equilibrium point here, and which is actually a unique one because this one is empty there. But that equilibrium point is unstable, right? And if I start doing the cobweb diagram, which actually, why don't I do that? here. So, you know, I just start iterating here. This was my initial condition, although my tablet doesn't like that. Okay. So I would go something like that. At this point, I'm even jumping here, but now I'm turning back. I'm jumping again here. Of course, for you, it would be impossible to reconstruct the exact same path that I'm reconstructing, precisely because this map turns out to have sensitive dependence on initial conditions. And there will be no obvious way, no obvious target. You will be doing this forever. You will not be settling down. It turns out this has infinitely many periodic orbits, but they're all unstable. So there will be infinitely many closed cobwebs, but they're all unstable. And in the end, you end up having actually a chaotic dynamics. This is not something I'm discussing now, but just to give you an idea, this is already in one dimensions. You can have very complicated dynamics, even from piecewise linear dynamical systems. And thus it's in contrast with the second class of systems, which are in fact more prevalent in science and engineering, the continuous dynamical systems. Remember, this was just examples for discrete dynamical systems, because I was talking about the evolution rules that you can have. But now we're going to number 2, which is the continuous dynamical systems, which are most often given, or most conveniently given, in a similarly explicit form, right? So I said, of course, you can define a discrete dynamical system in different ways, but the most sort of the canonical form for which we have theorems and which we'll have to work with is not an implicit relationship between xn and xn plus, but an explicit relationship. So the same game in continuous dynamical systems is somewhat similar, but also different. So the name of the game there, the most common form, is a differential equation, whereby your model is not good enough to tell you the actual evolution, but it should be good enough to tell you what the derivative of the evolution is, right? So this would be a first order ODE. So x is taken for some phase space, but in fact, it might actually be an infinite dimensional phase space, which in case this is not an ordinary differential equation, this is one way of say, writing a partial differential equation or delayed differential equation, but it has to be in this form. And t is again taken from E, and generally in that case, it would be say R, the real numbers. Okay, so the picture that goes with that is that when I determine the evolution of a continuous dynamical system, most often in science and technology, I don't have an immediate idea of the actual evolution. I have something which is intermediate and will give me, it all goes well, the intermediate evolution, but I have to work at that. So I cannot really immediately draw a cobweb type conclusion. This will be x and t at some time later. In fact, I should then consistently say this is x of tt. But one thing I immediately can relate to in terms of the geometry of the right-hand side, or the geometric implication for the trajectory is this. So this is supposed to be tangent, okay, to the trajectory. So this is f at xtt. So the picture we should have in mind is that the only thing I really know from this immediately is a tangent vector to the trajectory at each and every point in time, okay? But that's all I have. And that tangent vector actually, if I were to come here at another time, it would actually be a different vector generally, because this is the general non-autonomous context, okay? So this doesn't give you the evolution rule yet. What it gives you is it enables you to define an initial value problem. IVP, that's initial value problem, okay? Which if you have seen differential equations before, which I assume you have, then you must have seen this, that you basically, in order for you to have a specific evolution for your initial condition, you actually have to specify not just the differential equation, but the initial condition as well, right? And these together have a chance to give you a solution, because if you don't specify the initial condition, then generally you will have infinitely many different solutions to the equation, right? So that's immediately a difference relative to the discrete case, because nobody gives you the evolution equation directly. So you in fact have to assume that at this point, we're only assuming that very soon we'll have guarantees for that. We assume that there is a unique solution to this initial value problem. I'll get back to that soon, whether under what conditions is that a reasonable assumption. So the solution is of this general form, phi, and it depends on the current time, it depends on the starting time, and it depends on the starting point. So these 2 bits of data from here, okay? I need to assume at this point that it exists, and it's non-trivial that it does. So what does it mean for this to be a solution? It means that if you plug it into the equation, then you get an identity. So let's plug it into the equation, into the differential equation here. So that's what I'm doing now. I substituted this function, t naught, x naught at t, and I should get an identity. So this is identically equal, these two, and also it satisfies the initial condition. So phi t naught at t naught x naught is just the x naught that I have prescribed, okay? If that is the case, then I'm happy, because then I can actually, I have a handle now on the evolution rule, so I can define the flow map, which is all of a sudden well-defined. And our notation for that, this is a central notion in dynamical system, the flow systems, which will have, it's a mapping which has 2 times as indices, the initial time and the current time. And it's a mapping that acts on the initial condition. Once again, the current time here appears as a lower index in the mapping, and the initial time, and the current time is the upper index, right? So these are here parameters, but the map actually operates on the initial condition and maps it to the current position. So it would map it to phi t, t naught, x naught. That's the flow map. Very important notion in dynamical systems. It is inspired, it says flow because it's inspired by fluid flows. When you release a particle in a fluid flow, you mark its initial condition, say in flow visualization, and if you have a way of following that, say with a camera, then and actually recording all the previous positions, then it naturally flows. So the mapping that maps the initial point of that trajectory to the end, inspired by that, is called the flow map. But it is a mapping because it's not just applicable to that one initial condition, but it's defined for all of them, right? But it comes with 2 times. There's a window for which this is defined, okay? The initial time and the end time, okay? This is now what we would consider to be the evolution rule. So unlike in the discrete case, which is immediately given to you, this is the evolution rule for the continuous dynamical system case. Okay. Now, since it's not given to you a priori, I'll get to that soon, but it's not given to you. It's worth asking the question: is this a reasonably good evolution rule? Because for the discrete case, I just look at it by inspection and I say, okay, well, the evolution rule is smooth, right? Because that's how I define it. The evolution rule is what I immediately have a geometric understanding. In this case, hey, it's not smooth. It's piecewise linear, but not smooth, right? What can I say about this mapping, which is not explicitly given to me, and yet I'd like to know its properties? So the things that we will infer of the flow map, that it has some nice properties. Basically, the golden rule is it's as nice as the right-hand side of the ODE. There are general results ascertaining that. So basically, ft not t as a mapping is as smooth as f of xt. So that's good to know. So if you see some funny behavior jumping around in your solutions numerically, and it seems like, wow, that was a major jump, maybe my flow map, maybe is discontinuous. And I hear people making these inferences. Oh, maybe it's not smooth. You can very quickly see if that is the reason or not. You just look at the right-hand side. And as long as the right-hand side is smooth, then the solution map has to be as smooth as that. Maybe then you didn't apply enough resolution in time or in space. Okay, but if you refine, it's your numerical scheme that's not well resolved enough. Okay, so it's as smooth in time and as the right-hand side. And the other properties are this, that also it has group properties, which sort of very reasonable evolutionary properties. This is a 2-parameter family of transformations, and And it has these properties that make it nice. So first of all, f t naught is always the identity. And that you expect, right? Because that means you're starting at t naught, but you're not going anywhere. So the mapping should be the identity. That's good. And the other thing is that if you're stepping from t naught to a further time t2, then you have this sort of additivity, if you will, that you can first step to t1 and then step from t1 to t2. It seems like a trivial property, but it's not necessarily satisfied if the right-hand side doesn't have the right properties, or it doesn't fall in the simple category of classes, differential equations. For instance, you can have here an integral differential equation. There are examples of that, or some delayed differential equations that do not satisfy this. But as long as this function is nice, it's a finite dimensional operation and it's smooth, you will have, I just write it here, if f is CR are bigger than or equal to 1. Okay, well, I'll get to that, but this is just a review for now. And finally, if you ask, can I go back? And that was not a trivial question in the case of a discrete dynamical system, because if the function is non-invertible, as both of these are, then you cannot uniquely go back. The good news is that if your function here, the right-hand side, is smooth, it doesn't have to be actually one-to-one, the right-hand side, but as long as it's smooth, then the flow map will inherit that property, as well as it will become one-to-one. So even though the right-hand side is not a one-to-one function, the flow map will be. So namely, I can actually even say what the inverse of the flow map will be. So the mapping from t0 to t, which advances you forward, if you take just the inverse of that function, which means the inverse exists and unique, then you just get the evolution from t to t naught backwards. Okay, so if you are interested in going back, then no problem with that. You just take the mapping that took you from here to there, and there will be a unique inverse that maps you from here to there. Okay, there will be no branching at any point. Why is that important? Because that will have far-reaching implications when you evaluate, again, numerical results that people show to you or sketches of solutions. If you see solutions crossing each other, that violates uniqueness. So this is very important to know. Again, I'll give you examples. So this is the, so one conclusion is that under these conditions, the evolution rule is invertible. And smooth. So a special case would be, still under the properties of the flow map, when I move to an example, is that we also have a notion of autonomous systems for differential equations. So when the right-hand side df, the partial of the right-hand side with respect to t is identically 0, then it turns out that, well, what does that mean? It means that you have an equation, an ODE, which we call an autonomous ODE, ordinary differential equation. And what you see by inspection is that the way the system evolves, the way its derivative evolves, does not depend explicitly on time. Okay, so it doesn't matter whether you started this trajectory yesterday, or you're starting it today, or 2 years ago, or 10 years from now. It will not know about that. All it cares about is this how, in terms of its evolution, is how what its evolution will be dictated by its current state, and it will not be dictated by some sort of absolute time. Okay, so another way of putting that is that my evolution will only depend on how much time has elapsed when I evolve, right? Relative to because my solution will be time dependent, clearly. That's what it means. I have to differentiate it. But somehow the absolute time will not so much matter, but rather the difference between these two times. Okay, that will always matter, right? So in that case, a more formal way of saying that if I evaluate the solution at some time s, and I still formally use this notation because I have every right to attach an initial time to the solution, that will be just the same as if I subtract, if I check my solution t naught ago, but I also start the solution earlier. So instead of starting at t naught, I started at 0 from x naught. So it's going to be the same. So why not then simplify life? And whenever it comes to an autonomous equation, always start them from 0 because the evolution will not depend on the absolute time. So let's just call this one, generally speaking, t. Okay. And then let's just say that this is xt. And then I can simplify the notation so that I only depend on the initial position because it will be understood that the initial time is always 0. Okay. So that then enables me to simplify the flow map to an autonomous flow map. Which no longer requires that I carry 2 parameters, because I fix the initial time, it's always 0. So I will only carry 1 parameter, which is basically the time that has elapsed, right? Since the start of the solution. But what that is if you want to use the earlier notation, in the more general notation, I simply set 0 here and t there, okay? And that is just a mapping that takes you from x naught to tx naught. So that's a simplification for autonomous ordinary differential equations that you don't have to carry both parameters. You can always set the initial time to 0. Very importantly, you can't do this for a non-autonomous system, so the people make that mistake all the time. The evolution will be different if you pick a different initial time, okay? You need to remember that. Examples, because what can be, without really doing much theory or anything, are there any qualitative features that we can similarly extract by not, without doing any numerics or without really trying to, these are your two options. Somebody gives you a differential equation. You either try the little introductory ODE class that we all had and look up whether this differential equation falls in the category of ODEs that can be solved explicitly. I can assure you that if this is a new model of any complexity, it won't, or then you go numerics, right? This would be our initial reactions. Is there anything in between that actually gives me more insight with less work? Very often I don't care about the details of that evolution. I just want to know what's going to happen qualitatively, right? Is this a good model? What's the asymptotic behavior? And the answer is yes, at least in low dimensions, much the same way as in one-dimensional dynamical discrete systems, we're able to get that answer. Then as long as we don't go to too high dimensions, we can get that answer without actually taking the dynamical systems course, only attending 1 lecture or 2. How does that go? So this would be then an example 1. So example 1 to this would be, I take a classic model from biology, population dynamics. Okay, and this goes by the name of resource limited population growth. Okay, so the idea is that here I will take a one-dimensional variable, which is the population, and I take it from a phase space, which is populations cannot be negative, so it starts with 0. Okay, and I allow arbitrary large populations, so it goes to 0 to infinity. And I will look at, since it's a continuous dynamical system, I take the time, the evolutionary variable to be R plus. And if I get lucky, I can also, I don't know yet, I can probably take it for, I can also go back. In fact, if I have a good enough smooth model, then I can go back because I have just learned that the flow map will be invertible, right? So in fact, this is the one then, therefore, that I'm aiming to get. So what is a potential model for this? Well, for any growing population, the exponential growth in the absence of infinite supplies and no predators is a very good model, and is observed, by the way, right? So it basically tells you that the rate at which you grow is proportional to your current rate. There's nothing impeding your growth in that, your encounters with other elements of your species are unrestricted and the supplies are unlimited. Now, this is actually very much observed at the initial growth phase of almost anything, right? But sooner or later, you hit some bump. Either predators appear or the supplies will be limited. Okay, and the simplest way of modeling that is you start adding a penalty factor, which would essentially start reducing your growth rate. And the classic way of doing that is adding this type of function, and see and you know what? For simplicity, this is a general model, but it really starts making sense in this context when I said b equal to 1, right? And that's the most understandable then. Why? Because for b equals 1, when x is 0, so you're very close to your initial phase, growth phase of the population, then this factor is practically 1, right? So it's not really impeding your growth. But the larger x becomes, the smaller this factor becomes. So therefore, this will be smaller than your initial a. So you're paying a price for being more populous. Okay, so that's why it's a resource limited population, because all of a sudden you're competing for the same resources. Can I also do something similar, a quick assessment of the dynamics that I did before? So before I do that, we don't yet have the guarantee for this, so I'll just make this assumption that basically I have global existence and uniqueness of solutions to this ODE. So I don't have to worry about technicalities. So that means that this is an autonomous ODE. So this one parameter flow map, remember that since it's an autonomous ODE, there's no explicit dependence on time. I can just always set the initial time to 0. That's the time of observation. So this is well defined. For all t in R, which means I can also go back, so I can have a negative time. All right, so that's why I said, because once I have a flow map, it's invertible. Well, like I said, I already declared this, right? The reason is, perhaps I shouldn't say assume. Please forgive me the inconsistency. The reason I'm saying assume because I haven't really listed this theorem, but I already stated here that if the right-hand side is smooth, then I do have this assumption satisfied, so that this right-hand side is smooth. So I perhaps, if you excuse me, I replace that now with this, although I haven't formally stated this, but the right-hand side, which is f of x here. So this is actually C1, C infinity, but certainly smooth, actually as smooth as you want. So the global existence and uniqueness you have, and FT well defined. Well, what actually follows is not necessarily global existence. What may happen is that you have a solution running for a while and then it doesn't stop, but at least locally you have a solution. So the assumption here is still the global part. So that's why I put that there with a question mark. We'll see under what conditions you can send. Anyway, but that's sort of a technicality. Let's just see what we can get out of this, say graphically or without solving it. Well, we don't have the evolution rule. Okay, that was very convenient in the discrete case. What can I still get by? I can't do much. I mean, there's nothing about this to interrogate, so I have to interrogate that one in a meaningful way. So let's do that. What I'm going to do is just graph the right-hand side in the domain of interest, which is the positive regime. So this is 0 and this is x. Okay, and this I will just call y, but y will be f of x. So I want to graph f of x. Remember, b is 1. Okay, I haven't specified a, so again, I'm being fairly flexible about the model. B is 1, but I mean, I could have something else too. It's just for simplicity. If x is 0, then I'm not going anywhere because x dot is 0 then. So x is not changing. So if it was 0, then it keeps being 0. There's no evolution. So this right-hand side is surely going through this point, and that point will be a fixed point. Okay. If I graph the right-hand side, it will have another 0 at b, which now happens to be 1. So it's here. And other than that, it's an upside down parabola. So the way it looks is something like this. Okay, it's not so jagged, but maybe I can draw it a bit more forcefully. All right, excuse the jaggedness, but the beauty of these methods is that it doesn't matter that it's jagged, right? I can really just be hand waving. All right, so that's not the evolution of the system, but what I'm showing here is the graph of F, okay? What I do see immediately is that there are two fixed points here and there, right? And I do see that in between the sign of F is positive and here it's negative. It's also negative here, but my phase space actually ends there. So my phase space, since I don't have negative populations under normal circumstances, it ends here. So the phase space is just this part. Okay. So in fact, it's not the whole phase, the phase space, let's be precise. The Y is just a variable that I've used to plot Y. The phase space as such starts here, okay? And it goes into infinity here. Okay, so that's the phase space. I don't put an N over there, and that's the phase space. That's the phase space. Okay, now what can I conclude? The things are positive in this direction, so that means the right-hand side is positive, so x of t will be growing. So no matter where I start here, then I will be growing. I will be growing, no question. And it's always true up until this point, because at that point, I have a fixed point. So here I'm not going anywhere. Here I'm not going anywhere. But certainly in between, I'm growing, no matter where I am. The opposite is true when I'm here, right? Because the right-hand side is negative. So x dot is negative. So wherever I start from here, I have no choice but decreasing. So let me mark it that way. So I'm basically done. If I'm interested in the geometry of the phase space, what trajectories do, and the way we approach this in an introductory ODE class, we teach you tricks that will actually work for this equation. But if I add a couple of more factors, then it won't. Okay, and we teach you, then you have to use tables of integrals, and then you will get a complicated expression with all sorts of parameters. But if your interest is the qualitative dynamics based on your initial conditions, you're done. Because this is what's happening in the phase space. This is the geometry of the phase space. These are the possible outcomes. If you start here, you stay put, but it's an unstable fixed point. So it has the analog of, not the analog, it has this equivalent of the discrete system. So this is an unstable fixed point. At x equals 0, okay? What you have here is a stable fixed point at x equals 1, okay? And then we also see what another notion, when you have a stable fixed point, which is actually asymptotically stable or attracting also. In this case, we'll clarify these notions later. We also see what we call the domain of attraction. So basically all initial conditions will go to this equilibrium point that are not here. So what does this tell you about the resource limited population growth? If you want a global qualitative conclusion in terms of what will happen to a population that is subject to this, you see everything you needed to see. It says the following. If the population is non-existent, then of course it will keep being non-existent. But if you have the slightest population positive, it will start growing. And initially, clearly, it will grow exponentially. But afterwards, it will start saturating and it approaches the same fixed point always. All right. And if you want to translate that into what happens in the time domain, so you actually want a graph of the solution, you can already reconstruct that without necessarily all the details. How would that work? Well, now I'm showing things in time. This is no longer the phase space. Okay. So I'm going to plot x of t here, and time is here. And what I know that I will have two fixed points. One of them is at 0, the other one is at 1. So let's factor those in. This is going to be, this is 0 and this is 1. Okay, so what do those look like in the time domain? Well, in the time domain, a fixed point just looks like a flat line, right? And the other fixed point also looks like a flat line because it's not changing. I do put an arrow on it because I'm actually running along that curve in the extended domain or space and time. We, by the way, call this extended phase space in dynamical systems. Which is basically P cross E. So I take the phase space and I add my evolutionary variable. That's what I've done here, right? So use my phase space, use the evolutionary variable T. And what it does then tell me about a little bit about the evolution, actually a lot about the evolution of trajectory. So what does it tell me? If I start with a slightly positive initial condition, what's going to happen? Well, I'm going to grow, but my growth rate will be moderate, but it's picking up. Then it's reaching a maximum, my growth rate, my derivative, and it starts coming down. So I flatten out, right? So accordingly, I know immediately that qualitatively the solutions look like this, that they start out being almost flat, but I want to use a different color, right? And they pick up speed, and at halfway, they have the maximal steepness, slope, and then they flatten out again and approach down. Other solutions will be doing the same. Maybe they pick up later because I started them very close to this point, and it takes a long time for them to develop, and then also a long time to decay. Well, the decay rate will be the same. Now, what happens if I start over here for large initial conditions? Well, I will then just decay. So accordingly, the graph, let me move this x of t to here, just x, and the graph will be something like that for all the trajectories. They come down asymptotically. Okay, sorry. I hit the wrong button. And my sharing. Got it. I need to reshare. Sorry about that. Okay, I'm back. All right. And there's no intersection here. Because if I had an intersection there, then it would mean these solutions never cross, right? Because that would mean, that would mean that two different solutions are starting from the same point at the same time. And that would mean that would violate uniqueness in forward time. Also then if they cross, then in backward time. So I have to keep these separate. They cannot. So I cannot do that very well, right? But they're just asymptotically tangent to these two lines. Okay. Any questions on this? No. All right. Not so far. Now, if you say, all right, you got lucky, you were able to do this, but then the same approach works. So same approach works for any one-dimensional ODE. So let me just give you, again, I'm not even going to write down the equation. I'm just going to take the right-hand side and graph it. So this is going to be here, the right-hand side y, and this is going to be x. And let's just dream up a right-hand side, literally. I'm just sort of improvising here. So suppose that it goes like this, except that I want it to be thick. Goes like this, then it goes up, goes down, maybe it touches from below, just have some exotic stuff. Maybe it crosses x with a tangency, and it comes down and touches here, and then finally it goes down. Okay, at which point I just literally made this one up. Okay, so this is your right-hand side that I have just made up. No way you can solve this now explicitly. okay? Because this is a really complicated function. I'm not even giving you the details, just the shape of the right-hand side. It's not even perhaps a polynomial, okay? And what can I very quickly read off? Well, immediately, these are fixed points, right? Because at that point, the right-hand side crosses 0. And when the right-hand side is 0 here, that means you're not going anywhere. X is not changing. So you feed it back here, it keeps being the same number. So whenever the right-hand side vanishes, that's a fixed point for an ODE. Okay. These are not fixed points. Just because they're interesting points, they're not fixed points. But these are all fixed points. So that I know. And then I just very quickly do the sign counting. So I will say, oh, here things are negative. The right-hand side is negative. Right? Here it's positive. Here it's negative. Again, negative. Positive, positive, negative. Okay. And then I just follow up and use the same principle. Well, things are negative here in the first section, first part. So here I have decay. In the next one, the right-hand side is positive, so I have growth. In the next one, right-hand side is negative, I have decay. And here I also have decay. Here I have growth. Next one I have growth, decay, okay? And remember that we are actually done because the phase space in this problem, since it's a one-dimensional ODE, is just this line over here, right? So this is the phase space, P. And then let me just speed these up. And these are the fixed points, and I'm done. Complete characterization of what I'm gonna do based on my initial condition, okay? And I leave it to you to actually go ahead and see the time, plot things in the time domain. But very often, this is an exercise. So it's going to be now several levels of possible behaviors stacked onto each other, but you will just have to identify these fixed points as fixed lines in this diagram, right? And just work out one or two kinds of dynamics, right? So I can see that, and I can immediately read off that this is what? This is an unstable fixed point because it pushes me away. This is a stable fixed point. What about this fixed point? That's interesting, right? Any guesses on that? Because it pushes me away in this direction, but it attracts me in the other direction. So how would you characterize this? Stable or unstable? Or something else? Some people call this semi-stable. That's not an official term in dynamical systems. The end result is, how do you observe this? We want, as later on we'll see, a stable fixed point is something that if I perturb by a small amount, I'm still hanging around. Now that is not a given here, because if I perturb it in one direction, I'm going away. And we have to generally, the idea of stability, we have to allow for general perturbations, uncertainties. So all of us, all things considered, this is also unstable. This is also unstable. This is stable again. So again, let me just add these notions here. So this is a stable fixed point. I'm sorry, unstable. This is stable. In fact, attracting stable. So I'm not just hanging around getting attracted. This is also unstable. This is unstable. And this one is stable. And there's one in between, but you can figure that out. Yeah, it's unstable. Well, this is also unstable. I'm just using it. Okay. So now you have a tool that, again, you get a one-dimensional dynamical system. Doesn't matter how nonlinear, how complicated it is, you understand the whole phase space. It also gives you something for free. A conclusion is that a one-dimensional dynamical system, if it's continuous in time, no matter how complicated it is, it's never gonna really show complex or chaotic behavior, whatever chaotic means, because we haven't defined it yet. Why? Because you can have two kinds of behavior. You either are staying at an equilibrium point because somebody initialized you there, or you are on your way to another equilibrium point or to some equilibrium point, right? So anything else in between just goes to an equilibrium point. So no matter what you do in the meantime, you always settle down. So one-dimensional dynamical systems are such that either they are at equilibrium or are on their way to an equilibrium, and they are coming from an equilibrium, right? It doesn't mean, however, that you were at equilibrium and you're all of a sudden leaving it. That would violate uniqueness, because that would mean that this initial condition is a bona fide solution, and another solution would stem from the same point to its actual solution. That would violate uniqueness. So when I draw these arrows, you need to understand that that's a separate solution that never quite connects with this point. It just approaches it infinitely closely in backward time, and the other solution infinitely closely in forward time. It asymptotes to it, but never reaches it, okay? So the conclusion is that one-dimensional continuous dynamical systems, CDSs, are never complex or chaotic. That's a stark difference from one-dimensional continuous dynamical systems, in which you really don't have to work too hard to produce chaotic dynamics, okay? Even though the right-hand side is benign. Here, no matter how complicated this is, all right? No matter how complicated it is, you're never gonna get anything beyond what you've seen here, but you do get a full understanding of the phase space. Any questions on that? You could then ask, all right, well, what if I start increasing the dimensions? Do I have any tools for systems like that? And the answer is for a while. When you start looking at the dynamical system, which is a finite element code, right? That I'm not promising any quick solutions. I will have some tips for those who persist in the class and go to part 2. There's actually has been a tremendous advance in that area in terms of dynamical systems applied to very high dimensional problems such as beam oscillations or plates, but that's not the subject of this course. So there's good news there, but let's just take first things first. Let's go one dimensional higher. So I will use the pendulum equation, which I now introduce, although most of you already have an idea of the physical pendulum. And the physical pendulum, or some actually call it the mathematical pendulum, right? In fact, that's probably the right term. The physical pendulum is not so symmetric as the mathematical pendulum. But this is an incredibly relevant model for lots of things in nature and technology. And it's also realizable very easily. It's a pendulum which has a joint here, smooth joint in this first approximation. It has a mass and gravity is pointing downwards. I can describe its positions using an angular variable, okay? So I will use this a lot because it's probably the simplest nonlinear oscillator that you can think of and observe in nature, right? Anything that hangs, pretty much. Okay, so for that we have an equation of motion, and I rely on your knowledge of mechanics when I just blurt this out. Basically, F equals ma, right? Except that we have to use that would be the linear momentum equation. We have to use the angular momentum equation, which basically means moment of inertia of this point-like mass with respect to this point times the angular acceleration equals the torque of the force of gravity, which is acting here, right? This is the force of gravity, and the torque is the magnitude of this times the lever arm, right? So if you work that out, this is minus, because it pulls you back, right? So the positive phi is in one direction, but the torque exerted by gravity is negative relative to that. So minus mg alpha times sine phi, okay? That's the equation of motion. It doesn't look like anything we've done in this class, but I can bring it to a form like that. I cross out m, and I cross out the second power of L there. So what I end up getting first is F double dot equals minus G over L sine phi. It still doesn't look like the kind of first order dynamical system that we've been dealing with, but here's a trick that always works in mechanics to bring it to that form. So introduce some new variables, and x1 will be just phi, and x2 will be phi dot, and dynamic variable will be a vectorial variable, x1, x2. Why am I doing that? Why am I even changing variables? Note that this is a differential equation, but not of the first order. All the basic results for dynamical systems are formulated and are only true, in fact, in most of them for this form, but not for second order equations. But the good news is equations of any order, differential equations, can be brought to a first order form with this trick. Namely, you just write, well, by definition, x1 and x2 are related to each other by time differentiation, right? So x1 dot is just x2, and x2 dot, what's x2 dot? Well, x2 dot is just phi double dot, right? And for phi double dot, I have a formula here. So I use this formula, but when I see phi, I plug in x1. This is going to be minus g over L times sine x1. So there you go. In this case, the right-hand side here, f of x, where f is a mapping from R2 to R2. X is the element of the phase space, which is R2 itself. So that's symbolic representation of the ODE, which I have written out here. And I just left it open, x equals p. Okay, that p happens to be a two-dimensional space now. So it's in an appropriate extension, it does look like x dot equals f of x. So everything that I have said so far about dynamical systems like that, if the right-hand side is smooth, then you have a nice well-defined flow map which is unique, is applicable here. Okay. But things are not as simple to draw immediately because I can't really use the same trick that I did here, right? Because it's no longer a one-dimensional right-hand side. So what are the types of things that we can do for these dynamical systems? So I'm aiming fundamentally for qualitative analysis, which means saying things with certainty without solving the system itself. And very often, in fact, that answers most of the questions that you might have about a system like that. So first of that, I can still, look for fixed points, which are the simplest organizing centers of the dynamics. What are the fixed points? The fixed points are determined by points where the right-hand side vanishes, okay? So what are the points in the phase space on which that right-hand side vanishes? Well, certainly it has to be a double zero, right? Because the right-hand side of a two-dimensional function must vanish. So I know that they have to satisfy x2 equals 0. But the other component, so this has to be 0. And the other component is determined by the second equation, which must vanish as well. So when does it vanish? Well, when you have k times p for x1. So k is any integer. Okay. So if I now try to draw the little information I already have about the phase space, I already have some, right? Which is the phase space is now x1 and x2. And I've just concluded that I always have a fixed point here at 0, for sure. Okay. And if this is plus pi, then I have a fixed point there as well. And at minus pi, I have a fixed point there as well. And I could keep repeating this here, 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 except that nothing new will happen for a while. And the reason for that is that x1 is fundamentally a periodic variable, right? So basically, if I know what's happening here in this regime, then I can just identify these two parts of the phase space and repeat whatever I see. I can, whatever trajectory I see, I can just repeat it here. Okay. So why actually bother to draw an infinitely large phase portrait when it's perfectly okay just to restrict to this? Okay. So I could go ahead and identify these two ends. If I do that, to simplify my life, because of, f, the reason for that is f of x is 2 pi periodic in x1, okay? But when I do that, I'm actually introducing a new phase space, and the new phase space will not be R2, but the first coordinate will be varying on the circle. In our notation, usually the topological notation on the circle is S1. Okay, so it's a periodic variable. And I cross it with R, which is the velocities are not periodic. Just because the positions are periodic, it doesn't mean that the velocity will not be periodic. I mean, look at this equation, right? This is not recurring. The right-hand side does not have any periodicity in x2. It's growing linearly in x2. Okay, so now the phase space itself is what we call this topologically. This is the cylinder. And what I have done here, I could actually cut the plane here and wrap it up, and that would be the topologically proper phase space. Or I can just keep in mind that things will be repeating themselves and still keep the flattened cylinder here, right, for the purposes of analysis. So what else can I come up with? So this the first type of observation I can make is fixed points. At this point, I mean, I have to warn you that generally speaking, when you look for fixed points of a dynamical system, you have to solve for the zeros of the right-hand side. And in this case, this was easy. When you have a more complicated dynamical system, you may have to use a numerical method, say Newton's method, to find all the zeros. Nevertheless, that's an algebraic effort. It doesn't involve any integration. And in most cases, this will be instantaneous when you do it numerically. And immediately, you can plot the fixed points of the dynamical system and then kind of try to figure out how you can then build a big picture from this local information. Next thing, once you have a fixed point, next thing is you want to find out about its stability, and that gives you local information. Are things going to it? Are things going away? Are things oscillating around it? And then you try to push that information globally. That's hard to do in a high-dimensional dynamical system. We learn methods, but in 2 dimensions like this one, there are things that are helping you. So one thing that is helpful, in fact, that's also helpful in high-dimensional dynamical systems, is symmetries. If you see symmetries from the right-hand side, some of those symmetries will then have to be inherited by the solution. So one of the symmetries that, if you study the right-hand side in terms of its dependence on x1 and x2, the symmetries, I should say, of f of x, okay? So what are the symmetries? What I see is that if I look at coordinates x1, x2, and I also include time, then if I swap, what was the first one? X1 minus x2, but I also swap the time, which this function has no explicit dependence on time, but the equation has an implicit dependence on time. Look here, because of the derivatives. So when I swap time, so I start using minus t instead of t, okay? Then that will bring a minus here, because what used to be a derivative with respect to positive time comes out to be the negative derivative with respect to negative time, right? I can change the direction of time, but hey, the original system will say, okay, but if you can use the negative time as your evolutionary variable, but in order to get the original mechanics back, then I have to multiply the derivative by -1 because of the chain rule. Because first I differentiate with respect to the differentiation with respect to the old time is, let me write it out, differentiation with respect to the old time. I can think about first, differentiating with respect to the new time. But ultimately, the equation calls for differentiation with the regular physical time. I need to move this a bit. So by the chain rule, I'm sorry, I should write this out a bit more carefully. So I'm differentiating something with respect to time. Then that's the same as differentiating that same thing with respect to the negative time. But then I have to differentiate the negative time with respect to time, okay? And when I do that, this ultimately gives you minus d of the negative time. Of course, in practice, you could, let the negative time to be t tilde to rename it. So this is how you would do this. So this is what I mean by swapping to negative time. Same thing, I change the variable x2 to minus x2. I simply redefine the variables. But the point I want to make is that if you do this type of a substitution, then notice that the equation remains invariant. Why? If I all of a sudden use minus x2 here, okay, but at the same time I switch to minus time here, then my switching here to minus time will bring in a minus here, okay? And my switching, expressing x2 as negative x2 being, you know, x2 tilde. If I express x2 in terms of x2 tilde, then I will have a negative x2 tilde, but the two cancel each other out for minus, minus, and I haven't done much to x1, and the two changes here again cancel out because I have swapped to x2 tilde, it brings in a minus, and the change of time brings in a minus, so that cancels out. So I recover the same equation. Then we say that the system is then equivariant, some say invariant or equivariant with respect to this group of symmetries, okay? Now that is useful observation because even though you don't know what the solutions are, you say, okay, this is after all a pendulum. So if I do a positive displacement, then if it's not outrageously large, at which point I'm doing this, if it's just small, it's an oscillation, then chances are I'm either going this way or I'm going back if it was large enough. Let's suppose I'm going back, which means that my velocity is in fact is going to be decreasing. So somehow locally the solution does this. Okay. Generally speaking, an oscillation would do this in the phase space, right? If it's a damped oscillation, it will settle down. So this is not too outrageous to assume that. But if I know that, say, from numerics or intuition, then immediately I can say, all right, but then I will have the same solution, essentially, if I swap to x, the position to minus x2, which I'm doing now. I leave x1 unchanged. And I will have the same trajectory there, except its evolution will be opposite. So instead of involving growing x1s like that, it will be involving decreasing x1s because I also need to change the direction along which I'm traveling on the trajectory. Okay, so that's one symmetry. And there's another symmetry. You can also swap x1 to its negative counterpart. And time. So that's the second symmetry. Is that really true? Let's check. So here's my equation of motion. I swap x1 to minus x1, but I swap time. So that will take care of itself in the right-hand side because two negative signs cancel out. I swap x1 here to minus x1. That will change this minus to plus. So essentially I have a plus one, but I have swapped the time here. So that brings in a minus one. So that again cancels out. So the same sort of equivariance or invariance holds for the solutions. So practically that means that I can take this point here, but this time I'm swapping x1. Okay, so I'm going to go in this direction, say here. And I will have this piece reflected there because every x1 then gets swapped along the trajectory to minus x1. So I'm doing a mirror symmetry, okay? But instead of traveling downwards on that piece, I also have to swap the time again. So I'm going to be traveling upwards. And I can apply the same observation to the lower branch that I had here. And that will tell me that I have this piece again. And either you deduce it from the previous symmetry or from this symmetry, you then say, okay, it has to be like that. So even though it's a nonlinear oscillation, it still has this basic characteristic. Okay, so at least I know that. So that's one way. I haven't solved the equation, nonlinear equation, but at least if I get a solution and I plot it on the phase space, it has to obey this symmetry requirement. Okay. Now I can obey this symmetry requirement also in ways like that. Okay. And that turns out to be also a solution. But whatever I get as a plot, right, I cannot get something like that. Or I cannot get even something like that at this point, because it will not have that symmetry. That has to do with the fact that this is an undamped problem. All right, so I already can exclude a few things. Are there some other tools that I could use in the qualitative analysis? So we have used already fixed points, looked for fixed points. We have utilized symmetries. And one thing that often occurs in dynamical systems, especially coming from mechanics, but also in other systems, is conservation laws. So is there a conservation law here? Well, here you can use your intuition, or later we will also learn methods to find any potential conservation laws. This is an undamped pendulum. So for all we know from physics and mechanics, the total energy should be conserved because there's nothing that's taking away your mechanical energy. I did not assume any damping. So the total energy, which I'm going to denote by E, which is the sum of the kinetic and the potential energy, must remain constant along solutions. So we just need to know what the kinetic energy is, which in this case, for a rotational motion, it will be 1/2 times the moment of inertia of that point, ml squared, times the angular velocity squared, okay? Plus, I need the potential energy. If you go back here, look at what I can measure the potential energy with respect to, say, this position here, the rest position. I mean, I can pick whatever reference point I want for the potential energy because it's all about how much it changes. And for this particular phi position, this length, if you work it out, I have the mg times the L times 1 minus cosine phi. When phi is equal to 0, which is I'm at rest, that this it just gives me 1. And when it's not, then it just gives me this height times mg. So L times 1 minus cosine phi is the height. And that's how I get actually the force of gravity torque from this. Okay, so the next term here will be mgl times 1 minus cosine phi. And here I made a mistake because I'm showing the kinetic energy, potential energy, but that's not what I should be showing here. I should just be showing here the length, right? That's what helps. That I need this change in height, elevation, and then I need to multiply that by the force of gravity, right? Which is mg, okay? And I now can just rewrite it very quickly as a function of variables that I use in the phase space. So that means that this is constant. How do you verify this if you don't have the mechanical intuition that somebody tells you that this is preserved along trajectories? Well, the way to check that, right, is in this formulation is that you do the following, that you take E, I mean, fundamentally E is a function of x1 and x2, right? So you take dE, you plug in x1 of t and x2t, which you don't know because you don't know the solutions of these differential equations yet, but miraculously you were able to still evaluate this derivative. I'm checking the variation of the energy along solutions, right? So how do I do that? Well, I need to take the derivative of E with respect to x1, and I multiply that by x1 dot by the chain rule, and with respect to x2 and x2 dot. Okay, and the nice thing is that this will be a function of x1 and x2, but because of the ODE, this will also be a function of x1 and x2 because you use it from here. So x1 dot is just x2, and then this is a function of x1 and x2, but x2 dot from the ODE, again, is just a function of x1 and x2, notably just x1. And when you do that, very quickly, you'll see that this is identically 0. So in fact, this is preserved. I'll leave that calculation to you if you haven't seen it before. Okay, so the way you could use that conservation of energy in the dynamical system setting is that you go back to the phase plane portrait and you say, you know what, I just need to figure out what the level curves of the energy are, because if I start on one of them, then I will surely be confined to them for all times. So trajectories are contained in the level curves of Ex1, X2. Which level curve is defined by the initial condition? So if I want to, now that's something that, of course, if you're good at plotting level curves, now you could go ahead and do. I don't want to spend time on that. At this point, you could say, all right, let's use MATLAB and ask MATLAB to plot the level curves immediately. Much smaller effort than solving individual trajectories and trying to find out what they're doing in the long run. And I tell you another disadvantage of that in a second. So this is what we have known so far. This is plus pi, minus pi, okay? And what turns out to be the case is the level curves are closed like this. They're elliptical in this regime, and they're growing. It's supposed to be symmetrical. So, I mean, these all have to obey the symmetry conditions that I have already derived. My drawing is imperfect, but it still has to do that. Now, again, there will be a singular level curve when you do this plot. Singular in the sense that it crosses itself. And when you go beyond that level curve, and again, these are the fixed points, then things start to open up like that. And this will be directly from a plot. You can, like I said, if you're good at just plotting level curves of functions qualitatively, then here's the function with level curve. You can, it's not impossible to, in fact, we will learn how to construct this, fairly soon, I think, in this, not in this one, but in the next semester, by hand. Okay, but that's not the point I want to make right now. It's just that these are these the trajectories? Well, hopefully not, because if they are what I'm showing are the trajectories, then I have a serious problem here because they're crossing each other here. And that would violate uniqueness of solutions, because from this one initial condition, apparently two are going here. Except that I already explained that this is just an apparent violation. It's not a real violation because this happens to be a fixed point. So this is one trajectory, this is another trajectory, this is yet another trajectory, and there's no violation of initial conditions here. The other thing is that, so that's not precise to say that the trajectories are the level curves, and that's not what I said. The trajectories are in the level curves, because the level curves contain trajectories, but it's not precise to say that one level curve is one trajectory, but there can be several trajectories, in one level curve, and they cannot intersect because the right-hand side is nice. What's the evolution on these level curves? Again, it's a qualitative feature that you can read off very quickly from the equations. I just go back to the equations and I say, and notice the following, that this is true for any mechanical system, that the x1 and x2 have an intimate relationship. x2 is, after all, always the derivative of x1 in any second order mechanical system, which means that if your velocity is positive, then your position must be growing. If your velocity is negative, then your positional coordinate must be decaying. So when you look at these curves, such an evolution would be inconsistent with mechanics, because here your velocity is positive. Don't forget that this is the x2 coordinate. This is the x1 coordinate. At this point, your velocity is positive, right? So x1 cannot be decreasing. It can only be increasing. And that comes out from the equations. But just get used to the fact that in a mechanical system, whenever a trajectory is in the positive x2 regime, it's always increasing everywhere. And likewise, when it's in the negative regime here, so x2 is negative, that means you have a negative velocity. So your positions, no matter what, you have to be decreasing. Okay, so that immediately gives you the overall orientation. You can complete this picture without much thinking, just sort of mechanically. And there you go. It's a fairly complete understanding. So is this consistent with the physics? Yes. I mean, for small amplitudes, we have oscillations. And if you really give it a spin, then there will be rotations in the pendulum. Very interesting is this orbit in between, which, by the way, most likely you will not get if you just ask MATLAB or any other code to plot the level curves. It will miss this one, but it's absolutely crucial because it's so unique. Most algorithms miss that. They will just show you these types of curves, okay, and they will show you these types of curves. This is what you will get from MATLAB or from any other code. So you then, it's very helpful. And by the way, they will not get these points either. So what a generic plotting routine will give you is very convincing orbits here and those there. Then if you know dynamical systems, then you will know that, oh, wait a second, these have to shrink down to an equilibrium point here because that's the only way I can continuously complete this picture without trajectories intersecting each other, right? Because there's more and small orbits. So what I start right in the middle point cannot really grow in any direction because it would hit another orbit. It must be a fixed point. And likewise, there has to be some sort of intermediate level curve here that makes this transition to there because the flow map is smooth. Right. So as I mentioned, so if I start two initial conditions, then they kind of have to be close to each other at least finite times. If I see something completely different qualitatively, so one does this and the other one does that, there has to be something in between, which is a transition point between the two kinds of behavior. And then this is related to these fixed points. What connects them is called sometimes a separatrix, because it sorry about that, separates different types of behavior in the phase space, it's also called, another terminology said this is a pair of heteroclinic orbits. Okay, there's two pair of these, right? And they separate different types of behavior, and they're incredibly important, although just as the fixed points by themselves, they're practically unobservable. Because the probability of you giving an initial condition, which is right on that curve, relative to all the other possibilities, picking a point on the plane, is 0. Yet, this orbit is incredibly important because it really separates different kinds of behavior. That's why it's called separatrix. And these are the types of orbits that actually, in higher dimensional dynamical systems, create chaos, because these separation curves in a more complex nonlinear system can be incredibly complicated themselves. So even though you never observe directly these guys, yet they have an impact of growing a very complicated line of demarcation between different behaviors, right? That it is going to be really dicey to really identify borders of different behaviors, so that they look very benign and they're not directly observable. They're unlikely, to be observed. Same thing physically. So the pendulum does this, right? And if you get a larger spin, it does that. Do you think you will be able to observe the trajectory that does this, that for infinite times it goes to this point, and then in infinite backward times goes to the other point? Not really. Because for those long times, having no damping in the system is actually a bad model. Starts, even if it's even if the joint here is very good, over time, so you're going to start losing energy. So you're never going to observe this experimentally. Nevertheless, it's there in the conservative limit. Very important. Do I still have a time? I have another example which closes my set of examples and just basically shows you the power of the phase portrait, or the phase space approach, geometric approach. And that's going to be my last example. And then I really start going through more of the fundamentals in more detail, right? So I think I'll stop now because I don't have enough time to cover that last example, and I'll just take any questions you might have. I add that these are fixed points. These are types of behavior you already see in the system. And this is what we call periodic orbits. You may have heard the term limit cycle. These are not limit cycles, because a limit cycle is something that is the limit for other trajectories. It either attracts all nearby trajectories, in which case it's an attracting or stable limit cycle, or you can call it a repelling or unstable limit cycle, which means that it has a domain of repulsion. These orbits are not like that. These are just good old periodic orbits that are neutral with respect to each other. We don't call these limit cycles. So these are periodic orbits. And these are non-periodic orbits if I really just view them in this naive phase space, the kind of infinite, without accounting for the fact that X1 is repeating periodically. But if I then really go to my preferred physically reasonable phase space, which says that after all, the phi coordinate, it really repeats itself after a while, then in that phase space, they become periodic as well, because what they're gonna do, and they are evolving and they're matching up with the exact same exit point here. It has to have the same energy. So that repetition will be just here, you know? So those are also periodic orbits, but only in this periodic phase space. So this is periodic orbit on S1 cross R. So the way to imagine that is that this phase space is the cylinder, okay? So this is the phase space. P equals S1 cross R in this case. And the way then things will look is that I will just have one unstable fixed point here. I try to use the same colors. From that, I will start developing this heteroclinic orbit or separatrix, but it will come actually back to the same point. So the way it looks here, I'm not good at drawing this, but you know, I'm trying to do a reasonable, it goes on the other side, then comes back here. Okay, so that's the pair that we've been talking about here. Because that point is to be identified with that point. You will then have these periodic orbits, which I have drawn, you know, in black here, and they go around. Like that. Which means that somewhere on the other side of this cylinder, there will be another fixed point, the blue one, over there, which is surrounded by these periodic orbits. I don't want to draw too much, but it's on the other side of the cylinder. Maybe it's better if I put it there and then I plot these little orbits on the other side, because you don't see them on this side. And the whole reason why I've been drawing these is that you have then the outer periodic orbits, which do this. They come down here. Maybe I should use a different color. What do I have? So they come down here and turn back and then close up, right? So those would be these ones. Sorry. The other one, which is that's the spinning orbit. So modulo the problems with my drawing, sorry about that. This would be the geometry of the phase space when you do account for the periodicity. And then these are two different kinds of periodic orbits, but periodic nevertheless. They have different topological type, and the separatrix, that's like a figure 8, and it divides the cylinder into these two different parts. I stop here. I should have already stopped. But note that we really haven't solved the equation. This is not the classic differential equation approach. And yet you can really, when you have the right techniques, you can milk it and get a lot out. And if you were to solve this equation numerically, always welcome to do that. And I invite you to try that if you have your free time, and just solve it, the RK45, which is the OD45 in MATLAB. If that's your favorite tool, just give it a run. No problem, it will return your solutions. And if you're interested in the long-term dynamics of those solutions, you will run it for a long time. And you know what will happen then? These solution schemes are not designed to be energy conserving. They will start losing energy due to numerical imprecision. So your numerical solution will return the following. If you start from here, then maybe you come back incredibly close for the first time, but it's already not incredibly close. It does a minute difference. And if you start waiting long enough, this is what you will be getting from the numerics. And it's wrong for this system. but that's just the finite precision of the numerics and numerical dissipation brought in by the code. So somebody, I work a lot with students and postdocs, and sometimes I'm lucky to have very good students and postdocs, but sometimes they present things to you that, if you know the fundamentals, they just cannot be right. And that's a tremendous advantage to have once you work with a group of people and you have no way of checking hundreds of lines of code, right? And you just need to look at what they return, and you look at it and say, I'm sorry, I know you did your homework, but this just cannot be right, because it contradicts the basic principles that this equation has to satisfy. And that's where really nonlinear dynamics excels these days, because everything is data-driven, everything is code-driven, and people are not so much well-trained in the fundamentals anymore. They're incredibly well-trained in linear algebra and optimization, okay? And they have no control, reality check, whatever they, and they have very much trust in the code that they've written, right? And nobody has done anything wrong here, right? RK45, the OD4 is not wrong, but it's not equipped to deal with this system for arbitrarily long times. Numerical dissipation takes over. You need to know, however, that this solution to the system is wrong, okay? Because it violates conservation. All right, so that's my rant for now about numerical methods. Any last question or something, and I'll let you go.
There's one question. Would you mind repeating what you said about the separatrix and chaotic systems? Because, I mean, a single pendulum is not chaotic, right?
Sure, yeah. So two-dimensional planar autonomous systems, that's something that we will get to later, also cannot be chaotic. So one-dimensional autonomous systems cannot be chaotic. Two-dimensional continuous time dynamical systems, as it turns out, it's not obvious yet. That was a big celebrated result, it turns out, a few decades ago, also cannot be chaotic. And the pendulum falls in that category, it cannot be chaotic. What I was trying to say is that these separatrix type solutions that are forward and backward asymptotic to fixed points, or in fact, maybe even periodic orbits, turn out to have a major role in higher dimensional dynamical systems where chaos is conceivable and allowed in actually creating chaos and organizing it. That's what sorry if I wasn't more precise. This system is certainly not chaotic, okay?
Okay, thank you very much.
As it was a good question, because I probably created the wrong impression with that. It's a very important point. There was a question, numerical damping. Numerical damping just refers to the fact that these are, the numerical schemes are great, right? And that's what we do all the time, but they are approximate, right? So they don't give you an exact solution to anything, right? For the worst possible numerical scheme, which is also, was at least at the time when I was working in finance, that's the only scheme they were using for stochastic differential, is the Euler scheme, which basically means that you simply replace the right-hand side of this differential equation by its tangent, always just this tangent at each point, okay? That's an approximation. That means that you will be using the same tangent to advance the solution for a while, although the tangent actually changes. Now, these schemes tend to, when it's a mechanical system, they tend to just wash away energy. They're not constructed in any way. They tend to make the error in the wrong direction. And if it's a mechanical system with a conserved quantity, then that conserved quantity in mechanics will tend to be damped out by the scheme. In other systems, right, maybe the scheme actually increases that energy. So in that case, it would be negative damping. But for these systems, if you run this in MATLAB, you will find that that very complicated algorithm will slowly wash away your energy. It might take, 50 turns, depending on the parameters, but you will slowly spiraling into this because it's not engineered. It's finite precision. It will never return you to the exact same point, and it tends to eat away your energy. It's always a little bit lower. So that's what we mean by numerical damping or numerical dissipation. Okay. Anybody else? Good. Our first office hour is on Friday. If you have any questions about the material, and I anticipate that we will then have also a problem session already next week, which you're welcome to attend. So there will be some problems given out to you that are relevant to this material and probably some of the upcoming material. So it looks like we're done for today. Thanks for attending. See you next week. Have a good day.